Thank you for the introduction. Welcome to my talk. I'm Hyung-Seok from KAIST, and today I'm going to present a new and powerful JavaScript fuzzer called CodeAlchemist Semantics-Aware Code Generation to find vulnerabilities in JavaScript engines. And this is joint work with my colleague Dong-Hyun Oh and my advisor Sang-Kil Cha. Browsers process various inputs such as HTML, JavaScript, CSS, and so on. And there are various modules in the browsers dedicated to handle such inputs. If one of the modules is vulnerable, the web browser can be compromised by an attacker. In other words, attackers can get a shell by exploiting the victim's browsers when the victim visits the attacker's malicious website. This means web browser vulnerabilities are significant and can be very dangerous. And among all the browser's modules, JavaScript engine is particularly important for security because JavaScript engine vulnerabilities provide a powerful tool for attackers to bypass various defense mechanisms used by browsers such as CFI. So since JavaScript code is Turing complete, one can easily create, leak, or manipulate memory objects, which is typically not possible in other types of vulnerabilities. In addition, the price of JavaScript engine vulnerabilities is up to $200,000 in Zero-Dum, which is one of the most popular exploit acquisition platforms. Therefore, JavaScript bugs are very critical in terms of security. So our research goal is to automatically find JavaScript bugs. And there are mainly two existing methods, code-based analysis and fuzzing. Instead of analyzing complicated source code or binary code, fuzzers generate JavaScript code and feed them to JavaScript engine. Due to its simplicity, fuzzing is the most popular JavaScript bug finding method. So this talk also focused on the fuzzing. So to understand our technique, we need to first understand the overall structure of JavaScript engine and how they work. So at a high level, JavaScript engine consists of two modules, parser and executor. And first, the parser module converts the given JavaScript code into abstract syntax tree. And when it fails to convert, it raises a syntax error. And then the executor module interprets the ASTs and returns some result or some crashes. So also, the executor raises a semantic errors if the given AST is semantically invalid. Unless we generate both syntactically and semantically correct JavaScript code, JavaScript engine will simply reject our code, meaning that we cannot explore deep code in the JavaScript engine. So therefore, our fuzzer needs to generate both syntactically and semantically valid JavaScript code to effectively find deep vulnerabilities. So unfortunately, previous JavaScript fuzzers mainly focused on generating grammatically correct JavaScript code snippet, but not necessarily semantically valid ones. Those fuzzers are so-called grammar-based fuzzer and are limited by their semantics unawareness. So what do I mean by being semantically unaware? Here are some examples. And here we have a declaration of an array object which is syntactically correct. However, since the variable n is not defined here, JavaScript engine will raise a reference error, which is a type of runtime error. And similarly, the next statement is also syntactically valid, but raises a type error as we consider the non-variable as a function, even if it is a number. So as this example showed, current JavaScript engine fuzzers focus mainly on the grammar and producing a syntactically correct code snippet, but failed to generate semantically valid ones. So let me give you a more concrete example. We studied two most successful JavaScript engine fuzzers, jsfunfuzz and LangFuzz. Both tools were developed and maintained by Mozilla, and they found more than 5,000 bugs in major JavaScript engines. So the first one is jsfunfuzz, which generates JavaScript code snippet with predefined JavaScript generation rule. Since jsfunfuzz is an open source project, we download the latest one and ran it to generate 100,000 JavaScript code snippet in total. And each code snippet contains a series of try-catch blocks where each block contains 2.5 JavaScript statements on average. And note that, they always wrap the JavaScript statements with try-catch blocks in order to suppress semantic errors. So to measure how many statements are valid, we simply remove the try-catch wrapper and execute the modified JavaScript snippet on 4 major JavaScript engines. And guess what? It turns out that all the JavaScript code snippets raises runtime errors. And moreover, 90% of them were triggering errors after evaluating only 3 or less blocks. This means almost all the statements in the blocks were semantically invalid. But of course, this does not mean that jsfunfuzz cannot find any JavaScript engine bugs, because they will effectively suppress semantic errors with try-catch anyway. But it highlights that jsfunfuzz is extremely inefficient in generating semantically valid statements. And the next state-of-the-art fuzzer is LangFuzz, and it also did not care semantics. Unlike jsfunfuzz, we cannot evaluate LangFuzz because the source code of LangFuzz is not publicly available. So let's see how LangFuzz works with some examples. LangFuzz is a mutation-based fuzzer which randomly replaces JavaScript AST subtree with another subtree which type is the same with originals. For example, suppose that we give this code to LangFuzz, and LangFuzz mutates the first statement, which type is a variable declaration. And to avoid syntax error, LangFuzz replaced the first statement with another variable declaration statement. So the first statement is replaced with var x equals new string y. If we execute this code without any modification, it raises a reference error because variable y is not defined here. So therefore, to make the valid code in higher probability than just random, LangFuzz replaces variables in the mutated statement with others in the remain code. In this case, variable x is replaced with arr and variable y is replaced with I. But variable I is not defined in the scope of the first statement. So as a result, this code raises a reference error. And this example also highlights that LangFuzz is also semantics unaware. So our goal in this paper is to design a JavaScript fuzzer which generates both syntactically and semantically valid JavaScript code. So the key intuition of our work is to consider JavaScript code snippet as a Lego brick, where each brick has its own shape, and one can assemble the bricks in many different ways as long as the holes and the teeth of the Lego bricks can be connected. So in our case, we convert each JavaScript code snippet into a code brick as in the Lego analogy, and the teeth and holes of code bricks enforce certain constraints for each of them, and we can assemble those bricks as long as the constraints are satisfied. So with this key intuition, we propose a new JavaScript fuzzer called CodeAlchemist, semantics-aware code generation for fuzzing, has 3 modules: parser, analyzer, and fuzzer. First, parser module converts given a JavaScript code snippet into ASTs and fragmentizes ASTs to code bricks in the granularity of JavaScript statement. And analyzer module figures out assembly constraints of code bricks and merge code bricks and their constraints into code brick pool. And finally, fuzzer modules generate semantically valid code by Semantics-Aware Assembly. Now, finally, it is enough to know how we make code bricks and code brick pool. So before introducing how we did, let's see what is assembly constraint. So first, code brick is a snippet of a JavaScript code. It can be anything, but in our implementation, it is a JavaScript statement. And code brick may require some variables to be defined. We call such condition as precondition of the code brick. And the code brick defines several variables, and those variables will be available after executing the code brick. We call them post condition of the code brick. And both conditions become the teeth and holes for our code bricks, and we call them assembly constraints. Here is an example. This code brick does not use any variable. It means that we don't need any variables to execute this code brick. So precondition is an empty. After the execution, this code brick declares a number and an array buff, which are the post condition. So like this example, assembly constraint analysis is that for the given code bricks, figure out their preconditions and their post conditions. So first, by classic data flow analysis, the analyzer module easily gets required and available variables of code bricks. In the second code brick, a variable n is required because it is used as an argument of array constructor. After executing the second code brick, variable arr is defined and variable n is still available. So in the same manner, analyzer module recognizes required and available variables of the third code brick, but in this case, variable I is only available in the loop, so variable I does not belong to the post condition. And the next step is getting variable types. Due to dynamic nature of JavaScript, it is very harsh to statically infer variable types. So we choose the dynamic type analysis. Let's see how we did with the second code break. The analyzer module instruments the code break by adding getType function calls with required variable and available variables before and after the code break respectively. And after executing instrumented code, we can easily get variable types. So in the same way, we can obtain variable types of the third code break. And finally, analyzer module merges code breaks and their assembly constraints into code break pool. Then how do we semantics-aware assembly with code break pool? The main idea is to make precondition and postcondition of code breaks to be teeth and holes respectively. For example, the first code break has no tooth because there is no required variable, and it has two holes for two available variables. In the same way, the second code break has a tooth and two holes, and the third code break has two teeth and two holes. So with these code breaks, let's see how semantics-aware assembly works. First, randomly select a code break which does not have any tooth because there is no available variable. And now we have an integer hole and array hole. And again, randomly pick the code break which teeth are fit in the first code break holes and merge them. And after executing the code breaks, the integer variable and two array variables are available. Then randomly select a suitable code break like before and merge again. And finally, we get both syntactically and semantically valid code. If we repeat these steps, we can add almost infinite code breaks as long as assembly constraints are satisfied. But we are going to stop here for this case. So this is how our CodeAlchemist works. And now let me show the evaluation result about how valid generated JavaScript test cases are and how effective CodeAlchemist is in terms of bug finding. To answer the question, we collected about 63,000 JavaScript code snippets, and we picked the latest 4 major JavaScript engines: Checker Core, V8, JavaScript Core, and SpiderMonkey. And to check that CodeAlchemist generates semantically valid test cases, we evaluated how many test cases end without any errors. If test case contains many statements, it is likely to trigger some errors. So we measured the success rate of test cases based on the number of time-lapse statements. This graph shows the result. The green line indicates the result of normal CodeAlchemist, and the blue line indicates the result without assembly constraints. In other words, the blue line indicates the blue line is semantics-unaware, and the red line is for jsfunfuzz. As you can see here, the green line is always higher than blue and red line, and this result highlights that semantics-aware assembly is effective in terms of generating semantically valid test cases. But it is easy to simply generate semantically valid test cases. Let's imagine that the fuzzer generates only numbers. Then generated numbers are always both syntactically and semantically valid. So we evaluate CodeAlchemist in terms of bug finding also. So we first compare CodeAlchemist against jsfunfuzz and ifuzzer, which is a variant of LangFuzz. And we executed 3 fuzzers with 4 engines for 24 hours each. And as a result, CodeAlchemist found more bugs than jsfunfuzz and ifuzzer. Especially only CodeAlchemist found bugs in Checker Core and V8. Also, 1 out of 3 bugs jsfunfuzz found was also found by CodeAlchemist. This means that semantics-aware assembly of CodeAlchemist is more efficient than previous JavaScript fuzzing techniques. And finally, we ran CodeAlchemist on the latest JavaScript engine for a week. In total, CodeAlchemist found 19 unique bugs, including 11 exploitable bugs, which were confirmed by vendors. Additionally, we got 3 CVs. And some of you may wonder what this result means, because the number seems relatively small compared to other fuzzing paper targeting small applications and utilities. So let's assume that we ran CodeAlchemist on Amazon EC2. If we use high-performance server, which have 96 cores, it costs $5,500. And if we found 11 exploitable bugs and sold them to Zero-Diem, then we would get up to $2,200,000 in a week. In other words, we can be a millionaire in only 1 week. But as you can see, I'm not a millionaire because I reported all bugs to the vendors for free. But instead of the money, I got this paper. Yeah. So despite the good result, our system has some points to improve. Selecting a good seed can affect the result of CodeAlchemist like other fuzzers. And current CodeAlchemist employs simple random code break selection. But we could adapt advanced selection strategies. And finally, CodeAlchemist is now only supporting JavaScript engines. So it is straightforward to apply Semantics-Aware Assembly to other language interpreters or compilers. And all these issues could potentially lead interesting future research. So we will make our system available on GitHub to support open science in March. And we always welcome pull requests. And lastly, please refer to our paper if you are interested in more details about these items. And this is the end of my presentation, and thanks for the listening.
Bo from Northeastern. I'm wondering what kind of bug you find from those JavaScript engines.
I'm sorry.
What kind of bugs you find? Are they buffer flow or other kinds of?
Many of them was type confusion due to incorrect G compilation and like out-of-bound access. Yeah.
Okay, so and what's the consequence of those bugs? Is there any security consequence for that? Like native code execution or incorrect JavaScript behavior?
You mean the impact?
Yeah, impact. Yeah.
I said 11 bugs were exploitable, but it means we can do remote code execution with that bugs.
Okay, thanks.
Yeah, thank you.
Alex Cabravelos from NC State. So you mentioned in the paper JavaScript statements. Do you mean AST statements? Do you mean what do you mean by how do you define JavaScript statements? Lines of code?
Your question was what is the JavaScript statement?
Right.
According to the ECMAScript standard, JavaScript code is divided into statements and expressions. So I mean the JavaScript statement is in the ECMAScript.
Okay, got it.
Yeah.
So, and basically from your method, you increased the state of the art from 2.5 JavaScript statements to 10. Do you think in the future we can go to something more realistic than 10 statements?
I'm sorry, can you repeat again?
So with your approach with the semantics, we're still in very low JavaScript statements. Do you think in the future we will be able to generate more complicated samples based on your work?
Yeah, currently my approach is just support random code selection, random code break selection, but with machine learning or something other technique, we can select more efficiently. So it can be related to more generate complicated JavaScript code.
Thank you.
Mohsen from Arizona State. Can you please describe what kind of language features of JavaScript are you currently supporting in your implementation?
Can you say more loudly?
Yeah, sure. What kind of language features are you currently supporting in your implementation?
In my case, I use F#, which is the functional language made by Microsoft.
Oh, sorry, you didn't get my question. So what kind of language features of JavaScript are you supporting currently in your fuzzer? Like the begin function, declarations, or like different kind of features of JavaScript language. So it's very vast and enormous amount of features. What kind of features are you currently supporting?
I'm sorry, I cannot understand your question.
Okay, I can ask in offline. Sorry.
Hi, I'm Zheng Leong from NUS. So, I mean, this particular work basically kind of like identify what is the data dependency for a particular block and then change the block accordingly based on the data dependency. What are your thoughts on kind of like the extension of this work where we can get more in-depth kind of semantic meaning to the block instead of just purely data dependencies? Have you like tried or?
You mean the have I tried what I mentioned in the feature limitation?
Yes, more specifically, because currently it's just data dependency. Can we get more? Like for example, I know what are the bounds of certain data variables and things like that.
In my case, I didn't do that, but yeah, I think it is very interesting feature research. So yeah.
Okay, thank you very much.